In this lab, I will use a real-world model of a car in motion to demonstrate the concept of constant velocity using Newton's second law, and using this law, my goal was to predict the motion of the car. Using the programs Tracker and VPython, I was able to compare the actual motion of the car to its computationally predicted motion. As a result, I found that at first, the car followed the predicted path almost exactly. However, as time went on, the car linearly deviated from the theoretical model because it went at a velocity that was faster than predicted. I will talk more about possible causes for this later. Newton's second law is final velocity equals initial velocity plus the net force divided by the mass multiplied by the change in time, delta t. In order for an object to have constant velocity, the initial velocity must equal the final velocity, and so to have this, the net force must be equal to 0, thus canceling out the rest of the equation. Having no net force does not mean that the object is not moving. Rather, it means that the object moves at constant velocity forever, until a force acts on the object. This concept is actually explained by Newton's first law, which says that an object at motion stays in motion, and an object at rest stays at rest until acted on by an unbalanced force. With Newton's laws in mind, I took a video of the car at constant velocity. My plan was to test how closely the car's actual velocity correlated with its expected velocity. I uploaded the video to Tracker and formatted it with axes and the length of the car. Notice that the positive x-axis is on the right in the direction that the car is driving. I estimated the center of the car's mass in each frame, thus giving me the blue points that made up the graph and table to the right. To create the theoretical computational model to which the car's actual motion would be compared, I edited a code on VPython. The code needed to be changed because it was not specific to the car, and the equations for velocity and position were inaccurate for the purposes of predicting the future motion. I inputted the mass of the car, the ball's initial position, and its initial velocity, which was calculated by the initial change in position over the initial change in time. I also inputted the time of the last observation, as well as editing the initial velocity and the initial position equations to be accurate to the equation used, Newton's second law. All of these inputs allowed the code to create a model that should move in the same direction and speed as the car, and therefore model what the car would do if there were no net forces acting on it. Once these lines are edited, I can run the script, and it shows in model form the car driving and the graphic representation of the computational model. Using the data from Tracker and VPython, the graph of the actual car's position versus time can be compared to that of the computational model. You can see that the car starts out as expected, but over time it deviates, still at a relatively constant velocity, and moves at a higher velocity than expected. There could be many causes for this, such as the fact that the net force in the car caused it to move at a higher velocity. However, because of the fact that the graph appears linear rather than curved suggests that this was not the case. The most likely reason that the velocity of the car deviated from the expected velocity was because on Tracker, you must manually place a point on what appears to be the center of the car's mass for each frame. It is very difficult to be consistent with this, and especially as the car started to drive out of the screen, it was extra hard to find the center of the car because part of it was no longer visible. This explains why the car deviated from its expected path at later times rather than at earlier ones. One important question to answer is what would happen if the axes were switched. The answer is that the car would still be driving in the same direction and at the same velocity. However, our perception of the direction in which the car is driving would be switched. Another important question to answer is what do the findings mean? The comparison of the actual versus the experimental data showed that the car's actual motion was slightly off from the theoretical model, showing that there was variation from following Newton's second law exactly. This information also proved that any force at all will make it so the final velocity cannot equal the initial velocity, and therefore the object will not have constant velocity. One last finding from this observation is that it is impossible to predict how many forces are acting on the car from the surroundings because it is impossible to know every aspect of the outside uncontrolled surroundings. Some known forces that are acting on the car are friction, air resistance, and gravity. Therefore, unless the car was observed in a controlled environment that had absolutely no forces acting on it, the net force will not equal 0, and so it will not have perfectly constant velocity.